In this video, we'll discuss gas laws and some very basic properties of gases. Specifically, we'll talk about temperature and pressure. So to start off, we need to know what the kinetic molecular theory is. The kinetic molecular theory is used to predict the behavior of gases. So we know there's three states of matter: solid, liquid, and gas. We're going to really focus on gases, and the kinetic molecular theory explains the behavior of gases. Parts of this you're going to already know. So the first part says that gas particles are in constant, random, and rapid motion. In other words, gas particles are always moving. They don't have a set pattern, and they're moving quickly. And we'll learn later on that as the temperature changes, as the temperature increases, that would cause the gas particles to move even faster. The kinetic molecular theory also says gas particles are very far apart. We know this. If we think at the molecular level of a solid, the particles are tightly packed together. A liquid, there's a little bit of space, they're still touching, but not as tightly packed and organized as a solid. And then a gas particles, they're very, very far apart. So that's probably something you already know. Now, the last piece of this theory says that gas particles, since they're constantly moving, they're going to run into the sides of the container that they're in. They're also going to run into each other. And so when they collide with each other or the sides of the container, those collisions are called elastic collisions. What that means is when they run into things, they transfer all of their energy. So that all their energy is given to the particle that they collide with or the side of the container that they hit. Speaking of collisions, that leads us into pressure. By definition, pressure would be the force per unit of area on a surface. So if we wanted to put that into a formula, pressure would be equal to force over area. So this is our force, this is the area, and then P stands for pressure. So we can see if we increase the area, increase the denominator, the pressure is going to decrease. Some specific points about pressure, some things that we should know. If you apply the same force to a smaller area, there's going to be more pressure. And I said if you increase the area, there's less pressure. So vice versa, if you decrease the area, there is going to be more pressure. Pressure is actually created when gas molecules hit or collide with the surface of the container. So it says gas molecules exert pressure on any surface which they collide with. So the more frequently that the gas particles hit the walls of the container, the greater the pressure, which means they're going to hit the walls more frequently, more forcefully. That's going to increase the pressure inside of the container. Other things that dictate pressure would be the temperature that the gas particles are at. As we said earlier, the higher the temperature, the faster they're going to move. The volume of the container. If we make the volume smaller, there's less space for the particles to move in, so the likelihood of them running into the walls of the container are going to increase. And the amount of gas, or the number of moles of gas that we put in the container. If we put more particles or more moles of gas into a specific volume, there's more stuff inside, so the likelihood of the gas particles hitting the walls of the container goes up. So we could say temperature, just thinking about temperature, if we increase temperature, then pressure will increase because they're moving quicker, the particles are moving quicker, they'll hit the sides of the container more frequently. Volume, we talk about volume. If we decrease the volume, so we make the container smaller, then the pressure will increase. So the pressure will go up because there's less space for the particles to move around in. And the amount of gas, I'm going to talk about this as the number of moles. So if the moles increase, so we put more particles of gas in or more moles of gas, so if the moles go up, will the particles hit the sides of the container more or less frequently, assuming we keep the size of the container the same? Well, more moles is going to make more collisions with the sides of the container. So that means that the pressure would increase. So anytime the pressure is going up, which I have all of these going up, that means pressure is up, therefore more collisions with the sides of the container. And of course, when I say more collisions, those are gas particles that are colliding. So therefore more collisions, so let's put the word gas here, gas particles. They're colliding more often, more frequently with the sides of the container. Another really important thing that we need to know about pressure is that pressure, oops, sorry, I wrote all over this. I'll erase this now. Pressure always pushes. So pressure always is going to push. What did I mean by pressure always pushes? What I mean here is that pressure pushes from areas of high pressure to areas of low pressure. So we always go from high pushes to low, and that's of course for pressure. If you ever watch a weather map, there's H's and L's all over the map. That's showing you the atmospheric pressure. And you can predict the weather patterns by knowing pressure always goes from high to low. So science never sucks. It's always a push from high pressure to low pressure. Okay, there's something called atmospheric pressure. We all have atmospheric pressure on us right now. By definition, atmospheric pressure is gravity is pushing the atmosphere down on us or down on the surface of the earth. Now, we don't really feel the atmospheric pressure because we are assimilated to it. The pressure inside our bodies is equal to the pressure outside. So everything's equaling out. So we have lots of empty space, like our lungs and things inside of our body, and the pressure inside there is going to be equal to the outside atmospheric pressure. However, you might think if you swim down to the bottom of a pool, you feel your ears popping. The reason is because now you have the atmospheric pressure plus the weight of the water on you, and your ears have to readjust to the pressure that is now put on you. So your ears pop. Same thing when you go up in an airplane. As you go up in altitude or the plane rises, there's less atmospheric pressure at higher altitudes or at higher levels because there's less air or less atmosphere above you. So your ears try to adjust. Even though a plane has a pressurized cabin, it's not perfect. So atmospheric pressure is all of the air around us that is creating pressure. Gas particles are running into us, creating pressure on us. So let's talk a little bit about the atmosphere. The atmosphere is 78% nitrogen. So most of the air around us is nitrogen, almost 80%. Most people will think it's oxygen because that's what we're breathing in to survive, but it's actually not. Oxygen is the second most abundant gas in the air, and that would be 21%. Then, of course, there's carbon dioxide, a very small percentage, 0.03%. And then there's just other things like water, argon, different trace gases. And those all make up less than 1%. Now, if we think about this for a second, this nitrogen, I just want to remind us, that's diatomic, N2. The oxygen we breathe, O2. We know carbon dioxide, CO2. These things can change a little bit. For instance, carbon dioxide. If you are in a really densely populated area with lots of cars and factories, then the carbon dioxide is going to go up a little bit. If you're out in the middle of a forest, like a rainforest, you're going to have a little bit more oxygen present because the trees or the vegetation is releasing oxygen. And then think about water. On a hot, humid day, we have a higher percentage of water in the air. So these amounts can change a little bit based on your location, based on the weather. So it says atmospheric pressure at any location depends on the weather and the altitude. So when I say altitude, if you think about it, when you travel up high, like if you go to Denver or a city that has lots of mountains, you're the mile high city in Denver, you're a mile above sea level, there's less air above you, so there's less atmospheric pressure. Now, one thing to note, no matter the altitude, these percentages stay constant. There's just less total air. So it's still 21% oxygen in Denver, but it's because there's a smaller amount of total particles of gas because you're higher up, less pushing down on you, that it's harder to breathe. But again, it's still the percentage of 21% stays the same. And then weather, we said, well, depending on the weather, we could have high pressure or low pressure. And we know high pushes to low. A high pressure day would be a sunny, bright day, beautiful skies. Low pressure is when you have rain and clouds. So how do we measure pressure? Well, there's an instrument called a barometer. A barometer is used to measure pressure just like a thermometer is used to measure temperature. So here's what a barometer looks like. This barometer is going to be filled with mercury. So there's a tube, it's in a dish or a bowl. This dish is filled with mercury, and then this is also mercury up in here. The symbol for mercury is Hg. So there's mercury throughout the entire thing. And then there's a vacuum up here. This just means there's empty space. There's nothing in there. They've removed all of the gas. So it's just empty space. And so what happens is this dish area down here, this is open to the atmosphere. So there's air particles all over in here, and they're pushing down. They're going to collide with the surface of the mercury in the dish. The higher the pressure, so as the pressure is higher, there's a great force pushing down on this mercury. As it pushes down, it causes this to rise. So at high pressure, there's a high level or a high height of mercury. If I change the color and I'll just do low pressure, let's say that we put low pressure. So if I have low pressure, there's less air particles pushing down. So maybe the arrows are only this big. So there's less pushing down. So it's not going to force it up as high. So maybe this would be where it's at on a low pressure day. So what happens is the push or the weight of the mercury inside is going to have to level out with the push of the atmosphere outside. So basically, a barometer acts like a balance. The weight of the atmosphere, which is the air outside, is going to end up equaling out to the height of this column. Now, the reason they use mercury is because mercury is very dense. Mercury has a density of 13.5 grams per milliliter. So since it's so dense, there's a high mass in a specific volume versus water. If we think about water, water is only 1.0 grams per milliliter. If we use something that's low density, the height of this tube is going to have to be much, much higher. Okay, so this height is measured in millimeters or in inches. So millimeters of mercury or inches of mercury. And we want a liquid and we want a high density liquid, and mercury happens to fit that bill perfectly. So a barometer is going to measure the atmospheric pressure. Units of pressure. Well, if we look at a barometer, it's millimeters of mercury. Remember mm, this is millimeters. And Hg, that just stands for mercury because our barometer is filled with mercury. Other units, atmospheric pressure could just be ATMs. A conversion between the two, 1 ATM is equal to exactly 760 millimeters of mercury. So this would be a good conversion factor. So we know how to do factor labeling with different conversion factors. Here's a new one. Another unit of pressure is torrs. Torr is the same as a millimeter of mercury. They are equal to each other. So torr comes from the name Torricelli, and he helped invent the barometer, so they gave him his own unit. The metric unit or the scientific unit is pascals, PA. 1 ATM is equal to 101.325. Now this is kPAs. This is kilo pascals. For our pressure units that we use, or the pressure that we usually encounter for us in chemistry, it's better to use kilopascals. Otherwise, you're going to have a massive number. The other thing is, I like to round this number a lot of times just to 101.3 kPa. So if you want to do calculations as 101.3 instead of 101.325, that's fine. And then another unit, like if you have a tire or some of you might scuba dive, like a bike tire, a car tire, they're always measured in pounds per square inch. So PSI, that's a pound per square inch. Okay, so that's 1 ATM is 14.7 PSI. So to put all of these together, we would have 1 ATM, 760 millimeters of mercury, which is also 760 torrs, which is 101.325 or 101.3 kPAs and 14.7 psi. So these are conversion factors. And to use them, you can pick any two. They're all equivalent. So what I could do is if I wanted to, I could look at 760 millimeters of mercury. Go back a second. I could say 760 millimeters of mercury per, maybe I want to convert it to PSI, 14.7 PSI. And of course, since it's a conversion factor, you could flip it. 14.7 PSI is 760 millimeters of mercury, whatever way you need to use it to cancel out units. And again, you can pick any two of these. They could be two things next to each other. So you could do ATMs and millimeters of mercury. So 760 millimeters of mercury is 1 ATM, or vice versa. 1 ATM is 760 millimeters of mercury. So you can pick any two of these because they're all equivalent. So let's practice some factor labeling and converting units. You're gonna need a calculator out. So notice, just because it's not on the top of my page, yours is already there, I rewrote all of these conversion factors. So let's try a couple. So we're gonna take ATMs and we're going to millimeters of mercury. So let's factor label 0.830 ATMs, and now I need to get rid of ATMs, so they're going to have to go in the denominator, and I'm looking for millimeters of mercury. So let's look. ATMs, that's 1 millimeters of mercury, 760. ATMs cancel, and you're left with units of millimeters of mercury. So this would be 630.8. Again, I encourage you to calculate these with me. Really don't worry too much about significant figures. As we see as we go through the unit, these are going to be just small pieces of a bigger problem. All right, let's try the next one. 983.1 millimeters of mercury, and we want to get to kPAs. So to cancel out millimeters of mercury, we're going to need that on the bottom and kPAs on the top. So the kPa, well, we got 101.325. And again, if you put this as 101.3, that is totally fine. Don't worry about that. You decide how you want to do it. And then millimeters of mercury, well, that was 760. So millimeters of mercury cancel. You're going to have to multiply 983.1 by 101.325 and then divide by 760. So you should end up with 131.1-ish kPAs. Okay, there's a couple more here. I would suggest that you pause the video and try to do these to yourself to make sure that you can do them. When you're done, unpause and we'll check your work. Okay, so here is the work I have. You can see I got 76 PSI and 7,666 torrs. If you round it a little different, don't worry. You can see all my work right here. Notice I just made this 101.3 instead of 101.325. So if you did a 101.325, it might be a tiny bit different. Okay, one thing I should mention is that all of these conversions you do not need to memorize. We will always give you these. If you want to memorize them, that's fine, but it's not necessary. You don't need to memorize them. All right, moving on, we have something called standard temperature and pressure. This is called STP. This is going to be important. We'll come back and talk about it multiple times throughout this unit, but I'll put a star next to it because students tend to forget what standard temperature and pressure is. So please make sure you remember this. You have to know it. If we are at standard conditions, that would mean standard temperature and standard pressure, we are exactly at 1 ATM and 0 degrees Celsius. Now, when I say 1 ATM, well, that could also mean 760 torrs, right? Or 14.7 PSI or any of those other equal conversions. We'll just keep it at 1 ATM. That's how we usually write it. But you could say, well, standard conditions of pressure would be 760 torr. That's fine. That's true. Now, one thing to note, we are going to, instead of using Celsius for our temperature, we're going to use something called kelvins. So kelvins, we got Fahrenheit scale for temperature, Kelvin scale, and degrees Celsius. So kelvins, this is the temperature scale that starts at the lowest possible theoretical temperature. So we're saying we don't think it can get any colder than this, and that would be called absolute zero or 0 kelvins. So that absolute zero, this is the lowest temperature we can get, 0 kelvins. At this point, motion, or we could say particles, stop moving. So even those gas particles wouldn't move. We've never gotten this cold in the laboratories. They've gotten extremely, extremely close to absolute zero, but never quite there. But they predicted that that would be negative 273 degrees Celsius. Notice there's a degree symbol for Celsius. Kelvins is just capital K. There's no degrees there. And this is really important, kelvins. This is the unit that we're going to have to use for temperature on all of our calculations as we go through the unit, as we proceed forward. So we need to know how to convert between Celsius and kelvins. So here's a few formulas. 273 plus degrees Celsius is going to give us kelvins. Or if you have Celsius, we'll just rearrange this, solve here, subtract 273 from the kelvins, and that gives you degrees Celsius. Okay, so there's two new formulas for converting between Celsius and kelvins. You are also going to want to convert for Fahrenheit. So Celsius to Fahrenheit, this would be, the formula is 5 nines times degrees Fahrenheit minus 32. Make sure you do the order of operations. So you got to do inside the parentheses, then multiply by 5 nines, or multiply 5 and divide by 9. And for Fahrenheit, it's 9/5. Now this one doesn't have parentheses, times degrees Celsius plus 32. Okay, these two you don't need to memorize. We'll give you those. This one, 273 plus Celsius equals kelvins, make sure you memorize this. It's very easy. That should not be a hard one to memorize. And you're going to use it so often, it should be just ingrained in your memory. All right, let's end up doing, or finish up with 4 quick unit conversions. So if we want to go to Celsius to kelvins, so then that means we're looking for kelvins. So we could use kelvins equals 273 plus degrees Celsius. So we plug this in, 273 plus -10. Well, that gives us 263 kelvins. If you feel comfortable, pause the video and then check back after we're done. Or after you're done, you can see that you got the right answer. Okay, same thing here. Try this one by yourself. If you do this, you should end up with 375.3 Kelvin. So again, it would just be 273 plus 102.3. Okay, the next one. Now these are the trickier ones. Make sure you pause and try this by yourself after you see me do one of them. So we want to use, we're looking for Celsius, so we're going to use degrees Celsius equals 5 nines times degrees Fahrenheit minus 32. Again, you got to follow the order of operations. So this would be 5 nines times 109 minus 32. Make sure that you do this part first. We have 5 nines. 109 minus 32 is 77. So you're going to do 5 nines times 77. And you should end up with 42.8. Okay, let's try the next one. We're going to do kelvins to degrees Celsius. So if we're going to do this, kelvins to degrees Celsius is equal to kelvins minus 273. So we're going to have 5 minus 273. Now notice we're going to get a negative number. We get negative 268 degrees Celsius. That is okay. Degrees Celsius and degrees Fahrenheit can be negative numbers. Kelvins, if you get a negative number for kelvins, something is wrong. Okay, so now that we have Celsius, let's convert that to Fahrenheit. So we're going to want to use our Fahrenheit conversion or formula. That'd be 9/5 times degrees Celsius plus 32. So now just Don't have to worry about parentheses. We'll have 9/5. My degrees Celsius, I just calculated, negative 268 plus 32. So do this multiplication here. You have negative 482.4, and then you have to add on 32. So you should end up with negative 450.4. So really make sure that you practice calculating Fahrenheit to Celsius and Celsius to Fahrenheit. These two formulas, those are the trickier ones. So we'll give you lots of practice on these unit conversions, whether it's temperature unit conversions or pressure unit conversions. They're going to be a little piece of much bigger problems to come. So make sure that you practice all these.